Okay. So that brings us to the next thing, which is a review of linear approximations and tangent lines. I know just this example. I want to work through my example. Okay. So imagine that we have this function, ln of x squared plus 0.19. Some random function. So now, let's say that we are, let's say at x equals 1. First of all, let's say we want to figure out what f of 1 is. So let's say we have an actual point that we're going to know for a fact. Then we want to find linear approximation, L of x, also the equation of the tangent line, it's the same thing. And then we're going to approximate f of 1.5. Okay, so humor me, here we go. Okay, so first of all, what is the actual value at that point? You plug it in, and you get ln of 1.19. And let's just say I magically happen to know this answer, and it's about 0.1740. Okay, that means we know the point 1 comma 0.1740. So then, from there, how do we construct a linear approximation? We need to find the slope. We have a point. We also need to find the slope. So for that, you take the derivative, which looks like that. And we want the derivative at that point, so you plug in 1. And you work it out, and you get approximately 1.6807. Okay. Now I've got point and slope. So we can now turn that into the equation of the tangent line. So, and as you guys might know, there are two different ways to write this down. You can either write it in the point slope form, y minus y1 equals mx minus x1, and just write it directly like that. Or you can write it directly in like y equals form. So you can just say y equals y1 plus m times x minus x1. So in general, either one is like kind of fine, just depends on your preference. But here, since we're going to write it as a function, we're going to say Lx equals 0.1740 plus 1.6807 times x minus 1. Okay. And then to approximate the value at 1.5, you plug that into L of x, blah, blah, blah. You get 1.0144. Okay. And I just grabbed my calculator and I found out that the actual value for the function when x equals 1.5, you plug it in, you get 0.8920. So we were kind of close. We're off by a little bit. All right. So all this stuff, like I said, this is a review. This is stuff that I think you've seen before. I want to start talking about something that that I don't think you've seen before. What would everything that we've done algebraically, what would that look like on the graph? Wait a second. Not ready for that. Okay. What does this look like on the graph? Well, here we've got the graph of the function. And so the green point on the left, let me get my cursor. There we go. Okay. So this green point represents the original point that we're given where x equals 1. You know, the y value is 0.1740. This is sort of like our home base, our starting point. Okay. Then we construct the tangent line. So the tangent line is drawn in here. And then when you find the approximate value at x equals 1.5, what you're doing is you're finding a point on the tangent line. So it's this other purple dot, it's this purple dot over here. So that's our approximation. So we're saying approximately when x is 1.5, the approximate value of the function we said was like 1.01. Something. Okay. But what's the actual value? The actual value lies on the actual graph. So it's this green dot right here. So like we said, the actual value, the y value is 0.892. That's about where that is. So does that make sense? Okay. So now, so we just approximated, we built this tangent line and we said we want to approximate f of 1.5. What if we wanted to approximate f of 2? What do you do? I'm sorry? The slope of which line? The tangent line we just found?
Yeah.
Okay, so we don't have to do that then. We already did it.
Yeah.
Okay, so we have it. We have a tangent line, which is a linear approximation. So, okay, plug in 2. Okay, so you plug in 2, you work it out, blah, 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 and you get 1.8547. Now, in fact, f of 2, use a calculator, f of 2 is actually 1.4327. Okay, so you can start to see that this approximation is starting to get worse and worse. And what does it look like on the graph? It looks like that. So what happens as x values get bigger and bigger? What's going to happen to the quality of our approximation? It's going to get worse and worse and worse. Because you can just by looking at the graph, you can see that the graph is sort of peeling away from the tangent line. Okay. So what do we do? Do we just say, well, I guess that's the best we can do? No, of course not. We solve problems here. We can make a better approximation. How can we make a better approximation? Yeah.
Find a new tangent line that's closer.
Yeah. Nothing says that we have to keep using this same tangent line, this same slope. So here's what we're going to do. Once we have our approximation, so at x equals 1.5, our approximate value was 1.01. Well, we're not going to keep foolishly heading off in that direction. We're going to adjust. And the way we adjust is by figuring out what the slope should be now. So we know, well, at x equals 1.5, where are we? Okay, over here. So at x equals 1.5, we can say, okay, well, at 1.5, the slope should be, plug it in, and you get 1.2295. Okay, so at my point, my purple point was x is 1.5 and y is 1.01. But now I'm going to follow a new slope. My new slope is 1.2295. So now I'm going to use that. And I'm going to plug in 2. So using that point slope, I make a new equation. And now I'm going to follow that slope, and I'm going to follow that, and I'm going to plug in 2, which is this calculation right here. So f of 2 is approximately L, and this is like my new L. I'm sorry, that's my old L. L of 1.5 plus, I'm using the slope at 1.5, which is this new slope, 1.2295, times x minus 1.5. And my new approximation is 1.6292. Clearly, this is a better approximation because I'm not going off on that slope that I had before, which is clearly worse. I've got a new slope which is more accurate.
So we used the point we already found with the new slope?
Yes. Okay. All right. So at this point, you should be saying to yourself, well, okay, this sounds like a nicer approximation, but why do we need to make an approximation? We already know f. We already know the function. So what's the point of approximating something you already know? I'm going to tell you, because I know where this is going.
Maybe if we don't know f. I mean, if we have
Exactly.
an array of points instead of a line, so we want to create a line.
What if we don't know the original function?
As long as we know one initial slope and one point, we can approximate the whole function.
That's the idea. So what we're about to do now is actually going to set up basically the rest of the semester. I'm going to sort of, what comes now is sort of, I would say, an overview of, because this is basically the question that we're answering. And I'm going to talk about all the different ways you can think about this question, and then for the rest of the semester, we're going to sort of dig into these in more depth. Okay. So, and we're not going to finish it today. This is going to take like a couple of classes. So, here we go. Everything under the sun. All right. Suppose you know that f prime of x equals 2x. What can we figure out?
The
Ah.
slopes at every point.
Okay. So,
So we can
yeah.
we can technically find the line, but only the shape of the line. You don't know at what level the line would be.
Okay. So, you're all saying correct things, which I like. Okay. So, yeah.
Is that possible if you can move the projector? To the side.
You know, Professor, we're having a problem seeing, because we got a lot of heads in front of
Okay. So, we're going to answer this question in 4 different ways. So first of all, symbolically, you can ask the question, well, okay, what is f of x? That's the most direct and obvious question to ask, and it's the one that I think some of you already started to ask and answer. That's the first thing. Second thing, we can answer this question from a numerical point of view. We can say, well, is there just some way that I can figure out what f of 3 is? Okay, which is similar to what we were just working on. Second thing. Third thing, can we draw f of x? Okay. And the fourth thing is verbal problem, like a real world context. Suppose that you know the velocity is the function 2x. Then how far have you gone, or what's your distance or position after x seconds? Okay. So I just want you to realize for a second that all these questions are more or less the same question, just being asked in slightly different ways in slightly different contexts. Okay. So the first one we're going to talk about is symbolically. So everyone should be handy enough with their derivatives that when you see f prime equals 2x and I ask what's f of x, it's pretty straightforward to see without much thinking, oh, x squared. Okay. Well, sort of. Plus a constant. So if the original f of x could be x squared, it could also be x squared plus 1, x squared plus 3, x squared minus 7. Because when you take the derivative, constant goes away. So here's how we write the full answer. We write x squared plus c. So c is some constant, and it's referred to as the constant of integration. And the plus c will sit there until you know something else. So what if I told you, for example, that f of 1 equals 2? Now what can you do?
C is substitute.
Yes, or something. Yes. Right. Now you can you find the constant? Yes, you can. So you plug it in. When you solve it, you find that 1 equals C in this case. So given that fact, we know that f of x is actually x squared plus 1. Okay. So in general, when you solve a problem like this, you always have to include a plus c, and you can only find that plus c with that extra piece of information, which is called an initial condition. Okay. So when we solve this problem, what are we doing? We're doing what's called finding the antiderivative. Right? X squared, take the derivative, you get 2x. 2x, take the antiderivative, you get x squared plus c. Okay. So if f prime of x equals 3x squared, let's find the antiderivative. What is f of x?
X to the third plus c.
Right. So I'm starting you off with easy ones. You should have seen 3x squared enough times from taking derivatives. This one's pretty straightforward. Okay. So now I want to talk about being able to do this not just with easy ones, but sort of like ones that look in any different sort of fashion. Okay. So antiderivative formulas. Okay. So we already talked about if f prime is 2x. Let's see. You get f of x is x squared plus c. And what if g prime is x cubed? What's g? Okay. So I know some people have already seen these things and some people have not, but let's think about it.
1 over 4.
Okay. If you're going to take the derivative of it, what should be? It should be x to what power?
Well,
X to what power when you take the derivative will give you x to the third? So it's clearly got to be something x to the fourth. But it can't just be x to the fourth, because derivative of that would be 4x cubed. So we have to cancel out that issue. So instead of just x to the fourth, it's x to the fourth over 4. So when the 4 comes down, it cancels. And then plus c. That's the general idea. So here's the formula. Okay. Great. Antiderivative. That's fun. That's a rule. Let's make some more rules. Okay. So if f prime is cosine x, what's f of x? Sine x. Because the derivative of sine x is cosine x. Okay. If f prime is sine x, f of x is negative cosine x. Because the derivative of negative cosine is going to be negative sine. Okay. We can do this all day, right? Okay. So if f prime is e to the x, what's f of x?
E to the x.
This is so easy, right? Okay. Now I'm writing it like this. Now naturally everything has to be plus c. I'm writing down the most important part. Okay. Now what if f of x is 1 over x? Yeah. Did I say f? I meant f prime. If f prime of x is 1 over x, f of x is ln x. Great. Okay. Now what if f prime of x is secant squared x? Because the derivative of tan x is secant squared x. Okay. Let's see. Okay. And let's see. There's one we talked about yesterday, or last time I think. If f prime of x is 1 over 1 plus x squared.
Arctan.
then f of x is arctan of x. This is one we went over this derivative last time. Okay. So, if f prime is 2x cubed plus cosine x, then what's the antiderivative f of x?
Those are functions
Half
of
x
the-
sine, half x to the power of 4 plus negative sine. The sine x plus sine x, sine of plus c. No,
Plus c.
Yeah.
Right. Okay. And so let me just comment. I didn't simplify because I want to make a point. What do you do with that coefficient? Well, what do you do with the coefficient in front when you take the derivative? You leave it. So what do you do with the coefficient in front when you take the antiderivative? You leave it. Exactly. So you just really so the 2 stays, and you take the antiderivative of x to the third, which is just x to the 4th over 4. And now you can simplify. And of course the antiderivative cos, sine, and then plus c. Okay. And of course, we can go piece by piece when we take the antiderivative, because it works the other way around too. When you take the derivative, how do you take the derivative of this? You go piece by piece, one term at a time. So we know if we were to check it, we know it would work out and we get exactly the right thing. Okay. So this is the antiderivative. Let's see, there's another notation that I want to show you right now, which is commonly used, particularly in the textbook. One second. So if you say, I'm going to start with little f of x, what's the antiderivative of that? That's commonly written as capital F of x. So I'll just call it big F. Okay. So in my notation, I've been starting with f prime, and the antiderivative is f. But if you start with f, then how do we make notation for the antiderivative? We just call it big F. So this is just, I haven't taught you any math, that's just notation. So I could ask a question like this. If little f of x is x squared plus 3, find big F. That just means find the antiderivative. Okay. So typically when you see little f and big F of x written together, that means we're assuming that big F is the antiderivative, so big F prime is little f. That's just basically, that's our definition. Okay. Question? It's good?
That's big F prime or is big F? It's big F prime or big F?
Prime
Yeah, that one. That's the same thing as what you wrote on the note. Big F prime equals F. It's the same exact thing, or
Yeah. So big F prime equals little f.
it's the same thing on the top. The antiderivative is big F prime.
Where did I write it before?
The one, no, I'm just saying it's the same exact thing, or it's
Yes.
it's different?
Yes. It's just a question of notation. So notice that in the previous example, I said we have little f prime, find the antiderivative. So what's the notation for that? It's little f. But what if I start with little f and I say find the antiderivative? I can't say the antiderivative is little f. I have to make a new notation for that.
Big F.
And that's big F. So the derivative of big F is little f, the derivative of little f is little f prime, et cetera, et cetera.
The answer to that is 3x squared plus 3s over 3x squared over 3 plus 3x.
Okay, to fill in that answer, yes.
Can you example for the last one? For big F prime equals F?
Here's the example right here. If I label it, there you go. So big F is x cubed over 3 plus 3x plus c If you take the derivative of that, that's big F prime, that's just the same as little f, which is x squared plus 3. Okay. So my point is, don't get hung up in the notation. Just remember if you're taking a derivative or an antiderivative. Okay.
Well, why is that positive sign x?
Okay, well, let's check it. What's the derivative of sine x?
Cosine x.
Cosine x is sine x?
The antiderivative.
Oh,
Yeah, sine and cosine are going to mess you up because the derivative of cosine x is negative sine x, but the antiderivative of cos x is sine x. So don't get that twisted. Okay.
Flip. Flip.
I'm just so confused. You said assume that they were in together. That big F prime equals the little f is in together. So how is it in together in the example that you gave us? That x equals x squared over x.
Here I just said little f is this, find big F. So if you see a question like that, assume that find big F means find the antiderivative. That's the definition for what that means. When we talk about little f and big F, that's what we mean. Okay?
Big F and big F prime are different. They're different things. I think that's what it's getting. Like big F is big F prime. It's not.
Big F and big F prime
Are different things.
Big F and big F prime obviously are different things. Because if you have big F and you take the derivative, what is that? Big F prime. Right. Okay. Okay. So for now that is antiderivatives. So everything where we know what a derivative is and what the answer is, then if you're given that function and said, hey, what's the antiderivative, you know how to do that. Okay. Next, we're going to talk about answering the numerical question, what is f of 3? Okay. So once again, we're starting with our expression, f prime of x equals 2 of x. If f of 1 equals 2, what is f of 3? Now, remember that I said I want to do this numerically. So yes, I know we know how to solve for what is the function f of x, and we could use that. I don't want to do it that way. I want to do it a different way, because that's going to lead us somewhere different that's interesting. Okay. So how can we do this? Well, we've got
First find the antiderivative.
is what I don't want to do. So yes, I know we know how to find the antiderivative, but I want to do something different that's going to show us something else. Okay, so what we've got here is a point when x is 1, y is 2, and we've got a formula for the slope. The slope is always 2x. So we can use that to make tangent line. Okay. So if we just use our regular straight linear tangent line approximation, we would say, okay, f of 3 is approximately L of 3. And I sort of skipped ahead. I just sort of wrote directly the expression without writing the formula for L of x. So this actually may need some explanation. Okay. So let's remember that L of x, you can write this as, if you bring, instead of writing y minus y1, if you pop y1 to the side, this is like y1 plus m x minus x1. Is that fair? Okay. So, and this is one of the most confusing things in algebra, I think, which is sometimes we use y notation and sometimes we use f of x notation. So all I've done here is I've converted from y notation into f of x notation. Because what is, so let's see, so x1, well, we know what the value of x1 is in this problem, it's just 1. But what is y1 in this problem? It's 2, which we just get from taking f of 1. So f of 1 is this just the same as y1. Okay, that's the first thing. Second thing is m. Well, where does m come from?
Replacing one
It's
and
the
two.
slope. It just comes from saying what's the derivative at that value. So this is the same as this. I just plugged it right in. Okay. So. Okay, so now we plug all these things in. F of 1 we know is 2. F prime of 1 is just 2 times 1 from the formula for f prime, and then you've got 3 minus 1 in there. Okay, work that all out, and you get f of 3 is approximately 6. But again, we know this is not a good approximation. Why is this not a good approximation?
Because it's too far.
Yeah.
1 and 3.
Right. Going from x equals 1 to x equals 3, we've given, if you think of it graphically, we've given the graph a lot of time to bend away from the tangent line. And we've only used one tangent line. So this is not a good idea.
In fact, the slope changed from 2 to 6.
In fact, that's a really good point. Yeah, which actually goes back to what you were pointing out before. Right? So starting out, in our linear approximation here, the slope is 2. However, in reality, what is the slope at the end when we get to x equals 3? The slope is 6. So the slope has changed a lot. So we really should not be using a slope of 2 for this entire range of x values if we want a good approximation. So what can we do to get a better approximation?
Get a tangent line.
Move each time a point, or because we have to do it in intervals. We can't just go from the slope from point 1 from x1 to x3. We would have to do it in increments to kind of stay close enough to the line.
Right.
Take a limit. Try to approach to the point.
Okay. So I'm hearing lots of good ideas and also a good idea which is going to come up as well.
If I were to combine the two ideas and just take it the way it works with limit, so you take it's like the integral. You take the multiple little increments, and then you just combine them into an integration.
Yes.
And you know.
And that okay. Well, if you already took Calc 2,
No,
then okay.
That's how we solve in physics.
Yeah. Well, you're in fact that as everyone's going to see, that's what we're headed towards. Okay. But let's go literally one step at a time here. Okay. So as we said, to go just slope 2 the entire way does not make sense. So what's going to give us a better approximation is if we keep fixing what we're doing. So if we go a little distance, we should say, oh, the graph is steeper now, so my approximation should be steeper. So I said, let's stop. Let's correct our path every half unit. So starting at 1, we're going to use a slope of 2. But then once we get to x equals 1.5, I want to correct my slope. Then once I get to x equals 2, I want to correct my slope. When I get to x equals 2.5, I want to correct my slope, etc., etc., etc. So as far as writing out the expression, what does that look like? So first, we know we're going to start at our original y value, which we said f of 1 equals 2. So we're going to start there. And then we're going to use the slope. But instead of going 3 minus 1, we're going to say, well, I'm only going up to 1.5. So I'm going to do 1.5 minus 1. So this is going to give me my new, so just up to here is going to give me my new approximation at x equals 1.5. Does that make sense?
I don't get the 1.5 minus 1.
Oh, because normally we would plug in like our x value here. Like remember when I did the first bad approximation, I plugged in 3 over here. But what we're saying is we're not going all the way to 3. Our first step is going to stop at 1.5. So first I want to get my new approximation at when x equals 1.5. That's why I'm plugging in 1.5. So once I get to this spot, what am I going to do? I'm going to say, okay, I now have some value. Now I want to go from 1.5 to 2. Well, I want to do that using my new slope. And where's the new slope come from? The slope comes from whatever the slope is when x equals 1.5. So now I'm going to say, okay, I've got whatever y value that gives me, and then I want to add on. Think of this like a linear, just like a linear approximation. Using f, that's f prime. Sorry if you can't see that font issue. Let's fix it. Okay. So using the slope when x equals 1.5, which we know how to figure out, now I want to start at 1.5, and I want to go up to 2. So each of these little expressions says it's going to take me from an x value of 1.5 up to x equals 2. And then what do I want to do from there? Then I'm going to say, okay, I've got that y value. Now I want to use a new slope. I want to use whatever slope I've got at x equals 2. And then I'm going to go from x equals 2 up to x equals 2.5. So what we're doing is we're using the linear approximation formula, but we're only going half a unit in x at a time. And then after we go each half unit, we're fixing the slope. Okay. And so then finally f prime at 2.5 from 2.5 to 3. And then that's my last change in x. And then that brings us up finally to x equals 3. So what does this look like when you actually, so here I've plugged in all the numbers and done all the calculations. So for example, remember that what was the expression for f prime in this problem? We said f prime of x equals 2x. So for example, f prime of 1 is 2 times 1. F prime of 1.5 is 2 times 1.5, et cetera, et cetera, et cetera. So we always know what the slope is at any x value. Okay. So you work all of these out, you add it up, and you get 9. Wait, is that right? Yes, 9. Okay. And what does this look like graphically? It looks like this. Except for that part. Hold on. Okay. So I tried to use different colors so you guys could see. So let me try to point out a little more clearly. That right there, that's the initial point that you're given. When x is 1, y is 2. Next is that little green segment. That little green segment is the tangent line at x equals 1. And we follow that up to x equals 1.5. And that gives us some approximation, which I'm not going to keep track of, some new y value, which I don't care about right now. Then from there, we say, okay, I don't want to keep following the same slope. Now I'm going to use a new slope. Which slope? The slope at x equals 1.5. So I'm going to make a new linear approximation from there. And that is the red segment. So that takes me all the way up to x equals 2. Once I get there, we say, oh, okay, well, I don't want to keep following that slope. I need a new slope. So I use my linear approximation formula, but now I'm using the slope when x equals 2. And so that straight line is that purple line. So what we're really doing is we're following little linear approximations. Instead of just using one long linear approximation, which is the tangent line, we're using lots of little linear approximations. And we're going step by step by step. I think it's easiest to see that what we're doing is using little linear approximations if you think of the linear approximation formula in this way. You use some initial value, and then you add on m times x minus x1, where really x1 is the x value where you're starting at, and then the x value that you plug in is the x value where you're going to finish at. Well, that's what we're doing all along this way, except, well, we do this multiple times, not just one time. So we do this when x1 is 1 and then x is 1.5. And then we use a certain slope for that. And then we do it again, where x1 is 1.5, my new x is 2, and I've got a new slope for that as well. Then we do it again, where my x1 is 2, my x, where I'm finishing up, is 2.5, and I've got a new slope again. So that is what this is. Okay. So I wanted to show you one example. So this is sort of me talking a lot about how this actually happens. Now let's see it all real quick, one problem, start to finish, efficiently. Ooh. Okay, so this process of not just using, well, this process is called Euler Approximation. So if you just use the tangent line, it's like an Euler Approximation with only one step. However, in the previous problem, we used 4 steps. That would be called an Euler Approximation with 4 steps. So here, we're going to say we know the derivative, and we know an initial condition, f of 2 equals 5. Can we approximate a future value of the function? And that's what we're going to do. So the derivative f prime of x is e to the x divided by x. Again, sorry for the funky notation there, because it's typed out. Okay, let's approximate f of 3.2, and we're going to use 3 steps.
Approximating 3.2.
Yeah, so what x value are we starting at? 2. What x value are we finishing at? 3.2. And we're going in 3 steps. So how big is each step? 0.4. Exactly. So our first x value is 2. Our next x value is 2.4. X value after that is 2.8. And then we'll finish at 3.2. Okay? So what does this look like? Okay. So let's actually work this out. So f of 3.2 is approximately, we start with f of 2 plus
f prime 2 times 2.4 minus 2.
Right. Okay, so stop there. Does that make sense so far?
Yes.
So far, that's just like using a regular tangent line linear approximation. But we're stopping at 2.4, and we're going to course correct. Plus
f prime 2.4
Nope.
Hey, 2.8
Right.
times 3.2 minus 2.8. We go on over.
And do we go one more? No, that's it. Why? Because we needed to go 3 steps, and we've gone 3 steps. So this last term takes us from 2.8 up to 3.2. So we're done. Make sense? Okay. So that is this expression right here. And now all you have to do is just literally just plug in and solve. What is f of 2? We know that it's 5. What is f prime of 2? Well, it's e squared over 2. So we're going to have to use a calculator to figure that out. 2.4 minus 2, that's 0.4, et cetera, et cetera, et cetera. Sorry?
We are not to use calculator in this class, right?
Absolutely.
We can rewrite it in terms of, can be rewritten in terms of delta x.
Yes.
It's f of
Yes.
x plus delta x plus f prime of x plus delta x
Yes.
times delta x.
Okay. So Costa brought up a good point, which we're actually going to talk more about next time, which is every single time we wrote 2.4 minus 2, 2.8 minus 2.4, 3.2 minus 2.8. We didn't actually have to do that. You can make a nice notation. If you say that every single time I'm going to go forward by 0.4 and call that a thing. And that thing is delta x. Now delta x, you already know from algebra, right? Because when we used to calculate slopes, slope is delta y over delta x. Same delta x. Delta x is just change in x. Okay. So that was a side comment. To finish out this problem, calculator, do. And then there's your final. And there's your final answer, which is your approximation of what is f of 3.2. Let me also quickly point out that I gave you a really funky f prime of x function because I did not want you to say, oh, hey, we can just figure out what f of x is really easily. Did that on purpose. So that in this case, the only possible thing you could do was the numerical approximation. You dig?
Well, it's not that hard to take the antiderivative of that. It's just 2 terms.
Yeah, it is.
It's by parts. It's multiplication by parts. And then it's ln.
It's hard enough. Okay. Anyway, so this is how far we're getting today. Does anybody have any questions?
If only we could do that